start. So this course is Embedded Systems and EE3401. So we'll have a 4 credit course, and our schedule is today 10 to 11, Wednesday. Thursday will be 10 to 12. So at a stretch 2 hours. So this is initially will be means I will take theory part of that, but later on we'll be working this with simulators in this slot particularly. And then on Friday we have this 4:15 to 5:15. Okay. So what is our objective here? So we want to familiarize you with the architecture of 8085 and 8051. Now, question is that in industry or market, there are so many processors, and then these processors are almost very, this fast processors. But still, this is useful because what is needed for embedded system knowledge is to understand the architecture properly and corresponding assembly language so that we can code it and we can develop our system with very concrete grief. Otherwise, we'll be working like a following a blind box. So that we do not want here. So you want that you should be able to visualize the architecture inside these processors, and then you should understand the codes, instruction sets, and you can develop your circuits there. We also want to make you skilled programming 8085 and 8051 with their respective assembly language. Now, question is that this assembly language, if you see, that varies with processor to processor. Okay, then in market there are say hundreds of such processors, and do we want to learn or do we need to learn all the assembly language? And initially it may be this fearful that how can I learn that? But with experience, you will see that this assembly language does not vary drastically from one processor to another processor. So there are similarities, and you can, if you know, say 8051 or 8085 assembly languages properly, then you can extend that knowledge and you can learn the new things whichever you will come across later on. Then we want that you should be able to design an embedded system with this processor, and in future wherever you work or whatever you take as a processor, say the current processors like ARM or this FPGA based processors, you can do with ease. So only thing you have to replace this processor by the other processors. That's it, and you need to learn little bit extra things of those assembly language. Otherwise, the means majority of the portions of the instructions will be similar to these instruction sets. And you also should be able to develop embedded system for signal processing application, because our we will see after few means couple of slides that we can apply these for various signal processing tasks, and which is very essential because whenever you are going to work with systems, we also need measurement of some parameters or signals of those systems. And so, and not only that, while we are measuring, there are chances of getting noises into it. And so we need to filter it out, filter those noise, and that can be done digitally within the processor. So we should be able to develop that also. So this is a tentative objective we have planned. And with this objective, this will be our guidelines to expand these courses, and we can divide the whole course with these number of chapters, which is related to that following that objectives we have developed it. For suggested study material, I will suggest you to follow the data sheets of various chips like Intel 8085, 51, or for 51, we will particularly be interested in say 89S8252 or 51, and that will be using this 51 or 52 in during simulation. Then ADCs, DACs. Apart from that, you can also follow this book by Ramesh Gaonkar, Microprocessor Architecture, Programming and Application with 8085. So this book is very good for basic learning on this 8085. Then you can also read, apart from these ICs datasheet, you have to also read different other ICs which will be required time to time in our course, and during that time you should read that one. Then you can also follow this programming and customizing this 8051 microcontroller by Mike Predko. And you can also follow this computer system architecture by Maurice Mano. With simulator software, simulator for 8085 will be using, and protein simulator 5 will be using that one. Now here I want to tell you or I want you to understand that why we should study the datasheet, because till now we are all conversant and habituated with reading books only. Okay, and very often we if we find a book, a good book, we are confined to that book, but this will not be good for such kind of subjects where the every day we have to be updated almost, because in the market in 1 or 2 years new chips will be coming in, and the old chips will be fed means go taken out. So you have to learn new things, and majority of the cases at the time of launching of this processor, the books are not available because the applications or utilizations of those processors are not matured enough, and or we are not experienced enough to write a book on that. And therefore, what is needed, the only guidance will be the data sheets. Now, the data sheets will be of, say, more than 300 or 500 pages, and studying the data sheet would be boring. But if we go with these small data sheets of these architectures and so, and make us habituated with that, then later on, it will not be difficult for us to find the exact information which we want out of these 500 or 1000 pages, right? But you need a habit of that. Unless you develop that one, you will be very impatient to read it during the time of demand. Okay, and so now onwards, it is your task to become yourself habituated with datasheet reading, understanding, and applying those knowledge for developing your engineering systems. Is it clear to you?
Yes, sir.
Okay. So you need a habit change now onwards, that you should not ask me which book I should follow. Rather, you should ask means about something which you have read from the data sheet. Okay. Another point, whoever is having unmuted yourself, you just mute. During classes, be careful with that. Unless and until I'm asking you to unmute yourself. Now, regarding grading policy, we'll be following tentatively these lines. We'll be having quizzes, and that probably I will try to make it surprise test of 10 to 15 minutes, and for say 4 times or like that, tentatively, depends upon the time availability of time. So 15% weightage we'll be giving. Then we'll do with simulation test. That means whatever you have learned, whether you can actually develop this circuit and run that circuit or not. So 35%. Then mid-semester examination 25%, end semester examination 25%. This is tentative, and if anything changes from the administrations or my side, will be intimating you intermittently. So otherwise, this will be followed. So now, before we study this 8085 or 8051 architecture, we should be motivating ourselves to why we should learn this and how these are going to be used in our day-to-day life. Okay. And so we'll try to find the scope of the embedded system. So mainly we'll try to understand that where actually it is applied. Now everybody has seen, or most of you have seen, the washing machine and this automated one, where you can find there are user interaction. So you can input that how much water you want to put, how much means what kind of washing you want, whether you want a rough or whether you want a soft washing or not. Then the washing patterns, and then you want to also see that what is the status of that washing. That means how much time is left till we get the complete washing, and several other needs. And now what is there? So in behind these interactive panel, we have a processor which is doing interacting with the user through switches, through display units, and giving you the required information. So it's a means of user interaction. So we can utilize this processor and develop a user interaction system through keyboards or through display units. Then if you have gone into any internship, or you can find from different sources of informations that in case of say substations or so, we have different control rooms, and where we are measuring different parameters like voltages, currents, and etc. in different lines, different feeders or so. And there are so many indicating LEDs and other things. So we want to measure the some parameters, and then we want to set some values that say we want this voltage to be this value. If it goes beyond that value, then there must be some tripping of the circuit. So if there is a certain current which is going the set current, then the relay should be tripped for the overcurrent relay, like that. So we want to set, we can set it through the keys or buttons that we have just now seen, and then we can limit the values of say current and of a relay. Then we can set the display parameters, what we want to see. So the high voltage side or low voltage side of the transformers, or several other needs we can do. So we also want that after these observations or measurement of the current, if it gets beyond certain limit, the relay should trip. And what is the condition of that relay? That should also be shown on the display panel. So all these things we can do through the processor or digital system, processor based system or digital system. We have also, we can see that in biomedical applications, we can measure pressure, and that pressure values should be displayed. We can also start and stop these operations. Okay. the measurement, then display parameters. Now here you can see that while we are collecting those signals, so there are chances that it is noisy or distorted because of, say, whenever your user is moving its his or her arm, so there might be some disturbances in the measurement. So we need to take care of that, and that should be taken care within the digital mode, because now our processing system is within the digital domain. And so we can do that, all these signal processing tasks also in these. And this is not surprising because very often we are doing it with computers where we are actually doing with the processors. That is a Intel's nowadays this Intel, what is that? i7, okay, or something like that. So we want to, we can apply these for biomedical applications also. And therefore, we must be aware that these particular embedded system can be applied, or the processor based system can be applied to many fields, many other fields, which are not directly within the domain of the electrical engineering. Okay. So because we can work with signals, and that can be any type of signals, and we can utilize different sensors to convert those signals into electrical domain. Then if that is an analog one, we can convert it into digital domain using this ADC, analog to digital converter. And if required, we can also convert this output of this processor, which is digital in nature, into analog domain through this DAC, digital to analog converter. Okay. So we can see that it can be utilized for signal processing. Now you can see here this picture where people are talking in a crowd, and now you are the primary user and the other people are the secondary user. Now what we want at the receiving end, that we want to hear only the primary person's or primary user's voice, and so the remaining, the surrounding noise must be eliminated. And so this noisy signal must be filtered out at this end. So we can model that as if this primary user's voice is this xt, which is passing through this process of get the sensors, which is your microphone at the transmitting end or the primary user end, and that has certain model which produces the sound, this x of t, and then this eta t can be of the surrounding noise, and then it is getting out, and this yt is received at this end. This can also be, this eta t can also include any noise which may arise in the communication channel, which may be wired channel, and major means in this case we have wireless channel. So what we want in the signal processing domain is we want to filter. Now this means in engineering we call it filtering, but at the same time, if we go with the mathematical terminologies, we'll call it as a convolution. So filtering and convolution are and same process. And we can also have inner product, which is basically uh, instantaneous multiplications of these two signals and sum of that, and which we often use for computing the different transforms like Fourier transforms or so. And then we need peripheral interfaces, which are in this case is the microphone and the speakers. So that we need. And all these, so this whole process of computations, and then this, after getting this yt, we need a inverse system of these so that these disturbances gets removed. And that can be done using our digital processor. And we'll try to let you learn this, that this can also be done with this small or simple processor like 8085 or 8051. So we get this noisy one within this processor, we get a clean signal, and then this clean signal is output to the speaker, which the receiver or this user can listen to it. Okay. Any questions so far?
No, sir.
No,
Okay.
sir.
Okay. So I hope you understood these applications and you are motivated enough in this. Now we'll see whatever you may have learned in your control system. Have you learned the control system?
No, sir. We have it in this semester as well.
Okay, so you will see this type of figure very often there, where I have taken one such system, that the driving. So this car is our plant or system, and we need a signal which will drive this car. And what is that? The accelerator, right? So this ut can be thought of as the accelerator signal. And then once this accelerator signal is given, what effect we can observe? We can observe the increase or decrease in the speed. Okay, so this vt. Now, what we want that the speed, say for example, we want to have a cruise control of this car. That means automatically we want to control it depending upon the different signal available to it. So we are making it simple for the time being, that we are only measuring this velocity, and that velocity measurement can be displayed on the screen, can be digital or this type of LED based or LCD based screen, where the user can see. And so this display with this measurement, and then we get the velocity. Now the user may want a different velocity, just like whenever we want a different velocity, we say we want to increase the speed, we just turn the accelerator in a direction so that the more fuel goes in and we get the more speed. And so we can do it also. This is in user interaction. Through this, that we can set, okay, we want this 60 km per hour or so. And so this will check that whether this is matching or not. If there is an error signal, then it will invoke this controller. Now this controller, how will be implementing, that will be showing in the next slide. But at the moment, we just go with these, that this error signal it takes as input and produces the acceleration signal. So for example, say this 60 km, but velocity is 40 km per hour, actual one. And so there will be an error. And so the UT must increase the acceleration or accelerators valve. So more open this accelerator valves. So that way, now if it is found that it is 80 km per hour, but we want 60 km, so this error should be in a such a way that it will try to close the valve more rather than opening. And that way we can make our speed control of the car. Now, question is how we can fit our embedded system into this situation. Now, you can observe that this RT is a continuous signal, ET continuous signal, UT all are continuous signal. But whenever we want to introduce our digital processor into it, we have to convert these signals into digital domain. And so we can have this signal like that. So now we can give this signal as a discrete signal very easily. So this is Rn. Now you can notice that changes from RT. I have now given Rn, which is interacting, so directly going into the processor. So this dotted line with red color is the processor or our embedded system. Okay. And then the error generated is also discrete in nature. So our controller is digital controller, and it is producing a signal which is digital in nature or discrete in nature. And so, but for this car, this is a analog system. So we need the conversions of this digital signal into analog. So here we have the signal as UT, okay, and then this measurement is VT. Again, this velocity is the analog signal. So we have to convert this signal through this ADC into this VN, and then again, so this system will run for continuous time. Is it understood?
Yes, sir.
Okay. Now, I hope that we have understood that what is the scope of our embedded systems. That means how we can apply and what are the different needs of the signal, or the signals are to be applied into our embedded system. And we have covered more or less all the required domain where we can apply these. Now, this particular red line, dotted red line, which I told that this is our microcontroller or microprocessor. Okay. Now, this can be any of the available one. In our course, we'll be learning this 8085 or this 8051. But it is not mandatory that you should always use this. You can use any processor, whatever available in this market, like say ARM processors, and there are number of families of ARM processors. So not only a single one, but also say we have this M Cortex, or we have this this dual core model. So what it is called, say we have this AP core, we can say application processor core. Okay, we can also have multiple processor core. Now here, what is the difference in some cases, some of these architectures? So what we have to see that what are the different architecture inside this processor, and now how we can develop all these component, this digital controller and these, into this digital processor. Now, one thought we can put it here, that what is this simplest form of controller? So we can imagine that we have this PID controller, and now how this PID controller is developed. You can see, if you see, then they say En is your input and Un is your output, then your Un must be of say some Kp into En. Then we'll have some integrations over field, some field, okay, and that would be your En Dn, say, okay, sorry, and then, and we will have some coefficients, say 1 by ks or ks, which is the coefficients of the integration. Then we'll have this kd and this differentiation of kd. Okay, like that. And so you can see all these are nothing but these, say, one mathematical operations, multiplication. Here we have multiplications and summation, integration. Then we have this one. So here, while we are doing this, say, since this is in digital domain, so instead of that, we will be doing this summation operation, okay? And then these differentiations we can do using the difference equation. Okay. So we can do it sorry. Okay, let me see. So delta En, which is nothing but this say En minus En minus 1 and so. Okay. So here what we are finding, it is only following the arithmetic operations, and we can have, you will see later on that we have the instructions for arithmetic operations. Operations for all the processors which are available in the market. So what we need to do, we need to utilize those instructions to accomplish these operations. Okay. Any questions so far? I want this class to be interactive. So if you want to learn, you have to learn within the class period. And if you
Okay,
think
sir.
that you can learn it later on just by watching these videos, and at the time of examinations you will be in trouble. And that time don't ask me or tell me that I have not read properly or sir please give me marks or so. And always try to be motivated with the contents or the skill you need to develop in any subjects, not the marks. Because even if you get a high marks, you may not be skilled enough if you are not put your effort sincerely. And that will actually be problematic and you will be in trouble when you are in the job, in industry or so, a paid job. So be aware and be motivated that you should learn and improve your skill. And for that, if you have any doubts, you clear it immediately. So you can raise your hand if I am on in during my talk, and then I will try to answer all the doubts you have. Is it clear to you?
Okay, sir.
Yes, sir.
Yes, sir.
Okay. So we will see that signal processing and embedded system framework, how it works and what are the things we need to focus on. And that is not that everything what I am talking will be covered in these, but possibly we'll be going through all of these through our engineering this 4 years time. Okay. So with different subjects. So I'm trying to just convey that how we can link different subjects which you will be learning or which you have already learned. And now I am giving a brief idea on what is the signal processing is all about. Now, what is the problem in this case? That we can come up with different signal processing algorithms, and that can also be converted into an architecture. but all the processing techniques boils down to one concept, and which is widely used, and that is the basic concepts, in my opinion, is the filter. And now whether we have use the filter or develop the filter in our learning. So from our past learning, say we have studied the basic electrical engineering, or we can have this network theory or something like that, we can see that we, without a conscious awareness or without the becoming aware of that, we have actually developed a filter which we can see now. Now you have already read about, say, RLC circuit, right? Which are in series. Now say, for example, I have connected a voltage that may be VT, right? Now this VT, you have seen that this end is connected to some AC signal and like that. So only thing what I have done, I am just taking this and I am telling that this voltage is applied. This is nothing but this voltage. Okay. So I have not drawn this part, but this is actually the actual system. And now I want an output. So where I can take, so what I can do, I can take my output from here at the junction of L and C, or I can take my output from here at the junction of R and L. I can take it. For the time being, let us see that we are concerned about the output at the across this capacitor. So now my system becomes that I have the supply voltage at the input of R. So this is my input terminal. And then I have an output terminal which is linked to this junction of L and C. And now what is VCT now at this junction? We have all calculated, right? So you can see from here that now we have converted this L and C into corresponding frequency domain. So we have this j omega L, we have this 1 by j omega C, which we have already learned. I believe so. Is it not? What are these terms? This j omega L and 1 by j omega C?
Reactance and capacitance.
Yes, very good. Now, what is the effect? See, even if you do not understand maths in greater detail, you can understand this, the division. So if I increase this omega, this value will decrease. And this value will decrease means if, say, omega is infinity, this is a short circuit. And so whatever current is flowing with the frequency omega equal to infinity, that will all pass through this. It will be passed to ground, right? And so what we'll get, but if omega is 0 or closer to 0, that means lower frequency, this signal will not be passed through that. So what we'll get eventually, we'll get a low pass version of this signal. So where this so what we'll be getting here, only those components which are having this value as not zero, right? So the higher frequency all will be died down, and will only having these values for which this omega is closer to zero, and only some term which is having the significant amount of energy in this band. So effectively what we can develop with these, is a low pass filter. And if we want to represent this in frequency domain, which we have shown here, that these frequencies are present in this voltage, but these frequency beyond this WC are absent. And so we have, or we can realize an LP filter, low pass filter, using this RL and C circuit. And we have done it for a long time in our technology or engineering domain. If you see the old radios where we used to tune our frequency using a knob, and if you have seen behind the knob, there was a number of discs, and those are basically plates of the capacitor. And if you change the overlapping area of the capacitor, the capacitance value will change, and accordingly it will be tuned to. And for that, you have seen, I think, that there is the response of a RLC filter will have somewhere peak at some frequency, which we generally call the resonant frequency, and that will be our radio channel. And that also, the same concept can be transmitted to this TV channels also. So ultimately the objective is to match or tune that particular frequency using which that particular channel is broadcasting the data or any information. Okay, so what we understand that we have already learned the concept of filter while we have studied the RLC. However, it may not be highlighted. So you need to understand this. Now you also develop the same low pass filter effect with another circuit components along with these R and C. We can take the op amps. So operational amplifier, we in short we call it as a op amps. And here you can see inside the op amp we have actually external sources or supply voltages, say plus V and minus V. And so apart from these signal, we also have separate power in these. And so we call it as a active op amp based filter. So this activeness comes with the fact that these component, the basic component of this circuit is having separate power sources. Okay. In earlier cases, we didn't have any extra power sources inside this system. Okay. And here we have additional power sources, which is used for converting this signal with amplified power or the voltage. Okay. Now, what is happening here? So, is the op amp based circuit is taught to you? Hello.
Yes, sir. It was taught in analog.
Okay, very good. So that means you know that what is the ideal characteristics of amp, that there would be no current towards this input terminal, and these two terminals are at virtually at same potential because of the high impedance, input impedance. And so what we can find that this is basically the voltage at the ground. So this is 0 volt. Now, if you find the model of that, so which is the output. So this is basically the output of the op amp. If you see the op amp model, so you will see that this is AVD, and we have some output resistance, which is very small, right? So we can imagine that this is our VOT, okay? So in short V, and so if this is 0, and if we assume that this voltage is higher than that, so there will be a current through these two parallel paths. And then this current where it will go. So now if we apply KCL at this point, so there is no current in this direction. So the only current availability will be in these directions, and these two will be sum to 0 as per the KCL. And we can find what is the voltage output in that case. And again, you can see that for the higher frequency, what will happen? This path will have zero resistance, and this will go through this source and this R0 to ground. So now you should not get surprised that how these currents are going to ground. So it is through this op amp inside circuitry, and this is just a model, not the exact circuitry, that this is having a source AVD and then R0. And so for each and every high frequency, this is going towards ground, and therefore I will again get the only those components which are having the frequency below certain frequency value, which will be calling it as the cutoff frequency. Okay, so below this cutoff frequency, every component will have non-zero amplitude. Beyond the cutoff frequency, every component, that means this m plus 1 to say n, okay, so all these components will have zero frequency. So this will go to zero amplitude. Okay, and so effectively what we have found, we can design a filter circuit using op-amp based active filters. We can also design a circuit using passive RLC filter or RLC components. But what all are doing is the filtering operation. Now what we want a digital filter. So that means the digital filter is an alternative to the earlier realizations. So I want you to be aware of that digital filter is not the only solution, but one of the many solutions. Okay. And since we'll be working within the digital domain, that's why we are concerned about the digital filter. And so these we can design it with these, and so the similar concept will be we'll bring it here also. Now instead of taking this continuous signal, what we need a discrete signal, and that we'll call it as a discrete in time. Okay, so this is discrete in time. So if I am having a time scale, say t, and I am having a signal, say this. So what I am taking a value here, and the next value, instead of taking immediately, I am taking at say certain time Ts, capital Ts, which we'll be calling as sampling time interval, this value. Then I am taking another value at this instant, and that instant is 2 Ts. Then I will take a value at 3 Ts, and so on, this 4 Ts, and so on. So what we observe here, that we are taking the value. So if I represent this signal as say x of t, now if I take only these samples, so these samples which is implicit and fixed. So this TS is fixed. So what we can do, instead of writing this as NTS, we are only writing N, not so this TS is implied. So this is equivalent to VS of NTS. So only those values we are collecting. Is it understood?
Yes, sir.
Okay. But while we are writing, we are omitting this TS part and writing only VS NT N. Okay. Now it should take a number of samples. That means all these values at all these instances, and then it should produce another set of samples in all these instances or for all these instances, and then it should be clean signal. So this noise should be eliminated. Now, what is the noise? So noise we can assume. So this is our assumption. And since it is assumption, so it may vary with context. So it is not always true, but majority of the cases or the cases we'll be handling, this assumption is true that noise is having higher frequencies, is of higher frequencies. Now, if I assume that the noise is only confined to the higher frequencies, that means we can get certain zone in the frequency axis, which are corresponding to noise. Now, what we can do is, that means that we can find some cutoff frequency, or we can set some cutoff frequency below which is our signal. So this is our signal domain, and above which we have noise domain. So if I can remove that higher frequency component, and so effectively, if we can design a filter which is having this kind of response, where we have certain cutoff frequency WC, and within this band, all the signals are passing with its original amplitude. But beyond this band, all the signals amplitudes are getting attenuated ideally to 0. Then we'll get the signal version or signal component here, VRN, and removed with these noises. And so we'll get a clean signal, right? So what we understand from this discussion, that filter is the basic signal processing action or operation, and this is widely used. It is not new to us because we have already developed certain circuits with RLC components or op-amp based circuits, which can also do the same job. And the concepts, you can see now that this RLC domain, passive electrical components, the op-amp based circuit, active electrical components, the digital domain, the processor, all are different paradigm, different domain, but the concept of filter remains same all through these domains. So that means if you understand the filter operations at its abstract sense or conceptual level, you can employ that same thing onto different platforms. So that means these are nothing but the different physical instances of the same filter object. Now, if you have learned the programming, say object-oriented programming, C++ or so, you can see there is a concept of class object. and then you can instantiate that class objects. So in our case, this can be that class will be the filter, some codes are there, and then I can have say L1, which is again filter, but it is with RLC. Okay, this is analogous. Don't think this code can be written. Okay, then we have L2 is same, but now in this case RC and some op amps. Okay, then we have this L3, which is again different instantiation of the same, but now we are doing with processors like microcontroller or microprocessors. Is it understood?
Yes, sir.
Okay. Is it interesting?
Yes, sir. So looking at the applications, it looks interesting.
Yes. And to also to know that our app means this particular subject is only focusing on an alternative solution, isn't it?
Yes, sir.
Yeah. Now, how can we implement this digital filter into embedded system? I have said that this is alternative. I have said that about the samples, how we can get the samples, at what instances we are getting the sample. So between two samples, there is nothing. Okay, we do not have any informations about the signal. All right. Now, how we can do? So as we have seen last time, that if we can convert our operations into basic arithmetics, then we can easily implement that using the arithmetic instruction sets of the processor, right? And so we'll be trying to find that what is the filter actually is, how we can develop a abstract representation of filter. Now abstract representation means a mathematical representation of that. If we can do it, we can easily use that. And so in this case, what we can find? Now we'll talk about this low pass filter first. So what we can do, I have xt, and then I convert it into say frequency domain x of t, sorry, x of omega. And if I see in the graph that I have some values, right? And I take a threshold, say WC. And what I am finding, if I can do something like this, I take one window, which is my h omega. Now I have used this omega to represent the analog frequency. Okay, that means if I have t and if I convert it, so I think I can change this. Sorry. So this one, and so this is also omega c instead of that. Now, if I do all these values are 1 in this region up to omega c, okay, and this is h of omega c. So effectively what we are taking, we are taking a rectangular window in this zone, okay. So where from 0 to omega c, we have only one value of 1, and this is our x of omega. And so if I multiply these two, what we'll get? So if I multiply these two, what we'll get? We'll get the values But we'll get these values beyond this omega c and beyond 0, all are 0, right? And we'll get some values, say like this. Tentatively, not this one. Means I think I have mistaken it. It should not be like that. Just a minute. All values are actually this is showing in the modulus form. So this is mod of that. So all these values are in this zone. So which are the amplitude of the frequency component content in the xt. Okay, but what is our object? That now what we have seen, that this part is the signal which is having its own amplitude passed, because this value is 1, and the beyond this omega c we have the value all zeros. So essentially filtering in frequency domain. So operation in frequency domain. So this filter means multiplication. Multiplication between the signal and the system. This is called impulse response or in frequency response of the system. So multiplication of these two, and we get the y, which is filtered version. Remove the noise part. Now our question is, what is the corresponding operation in time domain? Because if I always go for frequency domain, I need to implement this conversion of this x of t to this one. So this is again a process. But we want directly it from the xt, and we want a corresponding impulse response ht, and then we want to generate the yt itself. How can we do that? And by the way, I want to ask you why this ht is called impulse response. What do you understand by this? Hello?
Sir, the response of the system for an impulse
Input. That means when the xt
is an
is delta t, then whatever yt will get yt as h of t. Okay. Okay. So today we stop here, that the frequency domain operations or representation of filter is the multiplication operation, and we'll again tomorrow we'll start from here, that the what is the corresponding time domain operation. Okay.
Okay, sir.
Hmm. Just a minute. Okay, you may leave now.